Hey, Honors Math 1, this is Mr. Roberts at Shasta High. I'm going to be going through the study team test for Chapter 2. This video is not for everyone. It's really intended for people who are kind of having a difficult time getting some traction in the course, and they like to go through and kind of look at things in a little bit more deliberate approach. If you just have a couple quick questions, feel free to stop by the class and talk to me, but also feel free to watch. So first four questions, well, actually the first question, 4 parts, asks us to decide if we're given enough information to determine the equation of a line. And for the first question, we're given literally a slope of -2 and a y-intercept of 4. So those are our two parameters, right? So we can immediately just write, yeah, absolutely, we're given enough information. The equation is y equals -2. There's our slope parameter times x, and then plus 4, our y-intercept parameter. Clearly enough information. Two things should happen on this graph. It should go through this point, 0, 4, and have a slope of down 2 over 1, down 2 over 1, down 2 over 1. And then once you have enough points plotted there, you should just draw a line and indicate that it is a line and it goes on in both directions infinitely. All right, part B, similar, except this time it says line B passes through a point at 2, 2. So if I go x is 2, y is 2, and I place a point there, I see that's all I'm given, right? So if I was given an x-intercept, a y-intercept, a slope pattern, right, or just another point, any of that would be enough to figure out the line. But as it's written, or as what we're given, there's just not enough information to determine a unique line. There's multiple lines that go through the point 2, 2, if that's our only piece of information. Part C, this line has a slope of -7, and it passes through the origin. So when I pass through the origin, right, we're given this point 0, 0. So we have, we have a y-intercept, right? We know our y-intercept is going to be 0, and we have a slope of -7. So you can say, hey, we've got our two parameters again. I can write y is equal to -7, which is our slope pattern, times x, plus the other parameter is 0, right? Our y-intercept parameter is 0. So if I'm starting here at this point, I'm going to go down 7 and then over 1. And to get a better view, I can also go up 7 and then backwards 1. So I have 3 pretty solid points there. I'm grabbing a ruler, lining it up, and once I'm happy with how it looks, I'm just going to pull a line through those. That was not great. Through those 3 points, and again, I'm showing with an arrow that it goes in both directions infinitely. The third and final one says, hey, here is a line that passes through 2 points, right? One of the points is at -2, 1, so I'm going to go back to -2, -1, this point. And the other point it passes through is 1, 5, so up 1, or to the right 1, and then all the way up to 5. So here's our point, and I'm going to figure out both our slope parameter and our y-intercept parameter algebraically. So I'm going to begin by calculating slope. So I'm going to look at the difference in my y values. So I'm going to treat this arbitrarily as the second point, and then the other one as the first point. So I'm just going to write 5 minus -1 over 1 minus -2. So I have a slope of 6 over 3, which looks like a slope of 2. So my slope is m is equal to 2. Next thing I'm going to do is, I could do it either way. I could either use point slope form, or I could find the y-intercept. I'm going to choose to calculate the y-intercept by solving this equation, right, for b. And I'm going to plug everything I know into it. I'm going to pick this point. So from that point, my y value is 5. My slope we just found was 2. My x value is 1, and y-intercept is b. So I'm just subtracting 2 from both sides, and I get that 3 is the value of b. So my equation is y equals 2x plus the number 3. And I can see that on here now that I look at this, right? I can go up 2 over 1, up 2 over 1. So it clearly hits at the point 3. But I practice all the algebraic steps because, we know that it's not always pretty. Just draw the line through those points, and we're done. Oh, make sure we indicate that it's a line. Next question. Given the input, identify the output of each function. So here you can see for each one of these, we're given what the value of x is that's going into the function, and we're asked to determine what the output is. So for this first one, I'm just going to go ahead and say, hey, I've got 2 times 3 plus 3, that's the numerator, over 2 times 3 and then minus 3. So if I rewrite that again, it looks like 6 plus 3 is on my numerator, and I've got 6 minus 3 for my denominator. So that looks like it's going to be 9 over 3, which is the number 3. So for part A, when I give that function 3, it gives me 3, right? The output would be 3. Second question. I'm given an input of -2, and I gotta be pretty intentional about this. So I'm using parentheses to show that -2 is the value that's going in for the place of x. And then I've got my -2 and then a place for x again. We're going to substitute in -2 also for this x. So both values of x are getting -2 placed in, and then there's a plus 5. When I square -2, I get a positive 4. And then I've got -2 times a -2, which is another plus 4. And then I've got plus the number 5. So I'm looking at 8 plus 5, or the number 13. So 13 is our answer to 2B. Let's go to our next page. For question 3, things have reversed here. Now we're being asked to figure out what value of x we would place in the function, to get these two particular output values. I know that my answer is correct once I place in the value of x I found into these equations and verify that it does give me the desired output. So one strategy is just take the equation, take the definition of the function, right? This function is defined as 4 times the quantity of 2x minus 5 and then plus 6, and set that equal to the desired output. So I can write the following: 4 times the quantity of 2x minus 5 plus 6, oops, close the parentheses there. We want that to equal 42. So we can do a couple of things. I'll go ahead and use the distributive property. Maybe it's not the best way, but I'll write this as 8x minus the number 20 plus 6 is 42. I'm going to add, I guess let's combine these. So if I've got a -20 and a plus 6, that's going to be a minus 14. So I can say 8x minus 14 should be 42. If I add 14 to both sides, I'm going to get that 8x is equal to 56. And then the last step, right? And sometimes I'm interested in how these things get backwards, but you can see x is being multiplied by 8. And if I need to get x alone, all I'm going to do is divide both sides of that by 8. And I can write it like this. I can write, hey, x is 56 divided by 8. And it's always nice to write that step down. Turns out that is a nice integer, right? We can divide that. It's exactly 7. So x is the number 7 is our solution for part A. The other thing I said we could do is just take that and verify it. So if I put 7 in there, that becomes 2 times 14. And if I have the number 14 and I subtract 5, I'm looking at the number. If I have 2 times 7, which is 14, and I subtract the number 5, I get 9 inside of the parentheses. So that becomes 4 times 9. And then when I add 6 to that, plus 6, it becomes exactly 42. So this value is exactly what I need. This is exactly the value of x that will produce an output of 7. The next one is a little bit, it might be premature. We'll get very good at this with time. But this is saying the square root of something is twice x plus, the square root of twice x plus 12 has to equal 6. Well, I know one thing. I know that the square root of a particular number, the square root of 36 is 6, right? I just know that from arithmetic. I can think about that by squaring 6 too and seeing, oh, that's 36. So one way of thinking about this is just simply like, hey, this thing inside of here, this 36, right? That's exactly what this thing, the 2x plus 12, has to be, right? The thing inside of the radical has to equal 36. So a way to write that down is you can say, hey, this 2x plus 12 must be the number 36. Therefore, 2x has to equal, if I subtract 12 from both sides, I get 24. And then if I go ahead and divide both sides by 2, I get x is 24 halves, which is x is the number 12. So I'll write x is 12 over here. But when I come back in, just to double check, if I go 2 times 12, that's 24. 24 plus 12 more is 36. And the square root of 36 is 6. So this is exactly the value that's needed to produce an output of 6. Next question. So let's take a look at these. These are, I think I'll focus in on each one, and I'll just write my answers here. I won't write them in the space provided. So what I see is I see a monomial being multiplied by another monomial. There aren't any other terms here. This is just one term. We're just going to rewrite it in a more compact form. One of the things we can do is we can commute things in products. So if I have 2 times 3, that's the exact same thing as 3 times 2. So one way to think about this is to start noticing that these are both raised to the first power. So there's no purpose for these parentheses, right? I'm not raising these to a higher power. So I can just start looking at it like this. I could say, hey, this is going to be the same thing as 4 times 3 times, there's going to be an x squared times another x squared. There's going to be a y to the first power, and there's going to be a y to the fifth power. So if I start looking at it, this is the y to the first, right? If I look at all the parts, I can see, yeah, I've got the number 4, I've got the number 3. I've got an x squared and another x squared. I've got a y to the first and a y to the fifth. So looking at all this, right, the first thing I notice is, oh, 4 times 3 is the number 12. And then I've got x squared times x squared. That's 2 factors of x times 2 more factors of x. So that's exactly 4 factors of x. And then I have a single factor of x times 5 factors of x. That's exactly 6 factors of x. 1 plus 5 is 6. So this simplifies to 12 times x to the 4th, y to the 6th. And if I pick any values of x to plug into that, not only will the original expression produce an output, but this simplified version will produce the exact same value every single time, right? These are completely equivalent to each other, and this is a valid rewrite of a more complex expression into this simpler form. Let's look at part B. So on B, there's some ones here, and I'm going to take a moment to identify those ones. 16 itself is 2 times 8. And I'm going to write that because I see there's a factor of 8 in the bottom already. The other thing that I like to do is if my exponents aren't negative, I'll typically just write down the smaller and I'll repeat it above. So you can see I've got here x to the 4th and I wrote x to the 4th to the top also. My numerator needs additional factors of x because I need a total of 7 factors, and right now I only have 4. So I'll just multiply by 3 more factors of x. So if I look at my original numerator, the original numerator is 16x to the 7th power, and that's exactly what my new one is that I've expanded, right? I've got 2 times 8, which is 16, x to the 4th times x to the 3rd, which is x to the 7th. What's convenient about the way I've rewritten this is I very clearly see this giant value of 1, right? So my denominator only has 1 in it. My numerator has 2 times x cubed, and that's the simplified version, right? This is going to be 2x to the 3rd power. There are no values left over in the denominator. It just completely simplifies to 2x cubed. Let's jump to C. Okay, so C, if you contrast what I did with A and C, there is an exponent that I'm raising the parentheses to, right? So this tells me I have exactly 3 copies of this thing that's living in the parentheses. And if I want to, I can write it out 3 times. I could say, hey, 3x squared times 3x squared times 3x squared. And that's definitely a legitimate way to expand this and then just go from there. But I could also just notice, oh, if I take 3, right, this factor, and raise it to the 3rd power is going to become 3 to the 3rd power times, and then I've got this x squared, and I can raise that to the 3rd power as well. That 3 to the 3rd is the number 27. And if I have x squared and I cube that, this is going to be 6 factors of x. So this, my final answer is going to be 27x to the 6th power. And you can see that's exactly what I would get if I was to just start with the expansion, right? 3 times 3 is 9, times another 3 is 27. And I can just count 1, 2, 3, 4, 5, 6 factors of x. So this is exactly what we have, although I did a terrible job of circling that. That's better. Right, and then the last question in this group, I do have this giant 1 in the form of a over a, so this can be gone completely. One of the things that I talked about, probably infrequently, but I have talked about an optional way to get rid of negative exponents, is to multiply by a giant 1 that contains the opposite of that negative exponent. So I can multiply this denominator by b to the 3rd, and I would multiply the numerator by b to the 3rd also. Now what that gives me is no change, right? This is going to be exactly the same because this thing I'm multiplying it by is the number 1, so it's going to be equivalent. But what's very convenient is if I look at my denominator, this denominator has this b to the 3rd, or negative 3rd times b to the positive 3rd. And when I multiply that, that becomes b to the 0 power, right? No factors of b. I'll expand it this way. It becomes b to the 0 power. Well, if I've got no factors of b, right, that's equal to the number 1. Anything to the 0 power is 1. So what I'm looking at here is in my denominator, there's just the number 1. In the numerator, I have 1, 2, 3, 4, 5 factors of b. And that's exactly what I'll write. I'll just write b to the 5th power. And I wouldn't write over 1 for my final answer. I would just write, hey, this is b to the 5th power. I have 5 factors of b. Next question. Solve each equation for the given variable. I always recommend doing a check. So I'm going to rewrite this portion of the equation. This is going to become 4x minus 8. And then don't forget I have a 2x plus 1 plus that 4x minus 8. And then on the other side, it's equal to 11. If I combine my like terms, I've got 6x, and then that's going to be minus 7 is 11. If I subtract, or add rather, 7 to each side, I have that this becomes 6x is the number 18. And then if I divide by 6, I get x is 18 over 6, which is the number 3. So for this first equation, x is 3. And again, taking a moment and just plugging in 3 here, like 2 times 3 plus 1 plus 4 times the quantity of 3 minus 2, and just verifying that it really does become 11 is such a liberating thing, because then you know you have the correct solution and you can move on. And if you don't, slow down and look at what's going on with each of your steps and see if you can detect your error. Next question, pretty straightforward. On the right hand side, I'm going to distribute the 6. I'll write 6 times x minus 30. On the other side, I've got 4x plus 10. I can take away 2x from both sides. No, I'm taking away 4x's from both sides. So 4x minus 4x is 0 on the left-hand side. Over here, I've got 6x minus 4x is 2x minus 30. I know that you've had teachers that say, hey, write this in between, but really, I think it looks a lot cleaner if you just say, hey, what did you do to both sides? You subtracted 4x. You took away 4x from the left-hand side, you took away 4x from the right-hand side. You can see what your equation was and what it becomes. The next thing I'm going to do is I'm going to add 30 to each side. When I add 30, this becomes 40 is 2x. You can just notate it like this. I just added 30 to each side. And then finally, I'm going to divide by 2. So 40 divided by 2 is what it becomes on the left-hand side. On the right-hand side, it just becomes x divided by 2. And of course, that simplifies to 20. So for B, we have x is the number 20. I had fun talking to some of you about your approach for this. Some of you did a great job of like multiplying by ones on the left and right hand side just to turn the denominators into the same thing. And then once the denominators were equivalent, essentially what you did was you just multiplied by that denominator then to make it go away. And it's kind of a good strategy. Another thing you can do is you can remember from middle school that these are proportions, right? Whenever you have something that fits the pattern where you just have a numerator over a denominator equals something over a numerator over a denominator, we have what's called a proportion. And we know that this product, right, is going to equal this product. So you can use that to rewrite these without the denominators. And we're going to look at more techniques for dealing with these things with fractions later in chapter 3, just because sometimes you don't have things that fit this pattern. You can have like plus another fraction, plus, and then this whole thing changes, and that this doesn't work. But if I just use the fact that this is a proportion, I can say, hey, 4 times x is equal to, and I'll just say 7 times the quantity of 2x plus 1. So it's a proportion. Those things are equal. Can I erase that? Yeah. And I just need to solve this the rest of the way. So I'll solve by distributing the 7. This is going to become 14x plus 7 is equal to 4x. I am going to do this. I'm going to take away 4x from both sides. Oftentimes when I see this happen on student work, they won't put the 0 there, which is really important to keep. 14x minus 4 is going to make this a 10x, and then plus 7. So I need my constants on one side and the variable with the x's on the other. So I'm going to subtract 7 from both sides. So if I subtract 7, this is going to become negative 7 equals 10x. And then finally, I'll divide by 10. So negative 7 over 10 is what x is. Our classroom calculators do a very efficient job of letting you check that answer. X should be negative 7 tenths. And now that we've seen that proportion, because if I see a proportion, again, a fraction is equal to a fraction, I'm going to keep using this all the time. So I'll just go 4 times 2x is 8x. Is equal to 3 times 8, which is 24. And if I take and I divide both sides by 8, right, this becomes 24 eighths, and 24 over 8 is the number 3. So x is 3. All right, if there's any questions about those or anything you'd like to discuss, please chat with me. Look at the structure of the work, right? I really encourage you to slow down, write neatly. Use a pencil that's easy for you to erase, and you can erase cleanly. The challenge is when you get an answer and it's not checking, to go back through and look at your steps. And the more you organize your work so that it's neat and easy to check, you're going to have a much better time of finding errors. And really, that's probably one of the biggest parts of our jobs, right, is to, once we realize we made an error, to find that error. So let's keep focusing on that. All right, next, 6. Evaluate these expressions for the given values. So I'm telling you what A, B, and C are, and I'm just asking you to evaluate these. For this first one, you'll notice I am squaring negative 3. So I'm going to use my parentheses inside, and I'm going to square something, and then I've got plus 11 times something else. That first thing that's going to go in the where A was is going to be the value negative 3. And for C, I'm going to place the number 10. So when I square negative 3, right, that's a negative 3 times another negative 3, which gives us positive 9. And to that, I'm going to be adding 110. And when I combine those, I get 119. So this is 119. For B, I'm going to use probably some extra parentheses. So here's my value of A. Again, it's A is -3. And then I'm going to be subtracting from that the number 4. That's what B is. We're going to square that result, add 1, and then add 5 times whatever C was, which was 10. So in my parentheses, I've got a -3. I'm subtracting another 4, which gives me a -7. I'm going to square that. And then I'll just write plus the number plus 51. So I'm just combining the 5 times 10 plus the 1. And this is going to be -7 squared is going to be +49 plus 51. And that gives me the number 100. So that expression becomes 100 when we sub in the values we have. Notice the use of parentheses. It becomes particularly important when you're squaring some things, right? It helps avoid some errors. Let's see C. On C, I've got the number -3. Oops, I'll put that in extra parentheses. I'm going to be adding 10 to that, and then -4 times open paren -3, and then plus 2 times B, which is 4. All right, so in this first set of parentheses, I've got a -3 and a 10, which is going to be a +7. And then I've got -4 times -3, which is going to be a +12. And I'm going to add a final 8 to that. So the 12 and 8 together make 20, correct. And if I add 7 more, I've got 27. So for this case, for this one, this evaluates to the number 27. It is 27. And then the last one has a quotient. We've got in our numerator twice B, twice whatever B is, 2B, plus C, which is 10, and then plus 2. And our denominator, we're going to have A, which is -3, and minus 2 more. So in that numerator, I see 8, 9, 10, I see 20, right? That's 12 plus 8 more is 20. And then in my denominator, I see -5. So if I take 20 and divide by -5, I get -4. So this last one is -4. Write each number in scientific notation. So again, the goal is to write numbers that are in that format of scientific notation have the exact same value as the number I see here. So I'm going to begin by placing a decimal right after the 3. So I've got 3.563. And I'm going to multiply this by some factors of 10. I know it's going to be positive because the number I've written down is smaller than the one that I had, right? I've only got 3.563, and I need to make this 356. So I'm going to actually multiply this by 10 twice. If I multiply this number by 10 2 times, right, 10 times 10, the decimal will move exactly to this spot, and the number I have will be equivalent. So A is 3.563 times 10 to the second power. This one, I'll put the decimal right here. It's 2.85. Now I can see that the number that I just wrote down is much larger than the number I was given with originally. And in order to make this number smaller, I'm not going to multiply by 10. I'm going to divide by 10. And we showed dividing by 10 by using negative powers of 10, right? So each negative power of 10 is equivalent to dividing by the number 10. I can see I need to divide by the number 10 1, 2, 3 times. So this is just going to be times 10 to the -3rd power. So this is equivalent to 0.00285. All right, next. Probably the most challenging part of this was just clearly writing down what you had and what it became. So it says I've got 11 Skittles per day. Skittles per day. And the question is, how many Skittles is that? And I need to change that into Skittles per second. So I need to move away from days. and I can see days are in the denominator, so I'm going to place days in my numerator. And I know that 1 day is equivalent to 24 hours. So I'm now looking at Skittles per hour. The next thing I need to do is move away from hours, because I want to land at seconds. So I can leave hours, I'm going to go to minutes. And I know that 1 hour is the same thing as 60 minutes. So now I'm looking at Skittles per minute. And I'm going to do it one final time. And I'm going to say, I'm going to put 1 minute. And that is the same amount of time as 60 seconds. Okay, so why are these giant ones? Well, everything I just multiplied by is equivalent to the same thing divided by the same thing, right? 1 day is the same amount of time as 24 hours, so that's equal to, this is equal to 1. 1 hour is the same amount of time as 60 minutes. Something divided by itself is 1. And 1 minute is the same amount of time as 60 seconds, so that's also equal to 1. So 11 Skittles per day times 1 times 1 times 1 is still 11 Skittles per day, but my units are going to change. So if I look at this, I can see I've got days that are going to cancel with day. I've got hour that's going to cancel with hour, and I've got minute that's going to cancel with minute. And the only units that remain are, for time is going to be seconds, right? And we still have our Skittles. So let's write this all down, right? In our numerator, we've got the number 11. And then I can write these. It's times a 1, times a 1, times a 1. In my denominator, I've got 1, because it was 1 day, times 24 hours, times 60, times 60. And again, the only units that are left are Skittles per second. Now, when I grab my calculator, if you don't get this number immediately, right, you've got to be careful about using parentheses, because you really need to take the number 11 and you need to divide it by that entire denominator, which is 24 times 60 times 60, which is 86,400. So you can write this, it's going to be 11 divided by 86,400. And when you do that, 11 divided by 86,400, you get the following number. The following decimal, you get 0.001273, and I'll stop there. There's more digits, but I'll stop there. So this number is Skittles per second, but it does say write your final answer in scientific notation. So I'm going to go ahead and write 1.273, but I can see that the number I just wrote down was very large compared to what it needs to be. It needs to be 0.0001273. So I'm going to be dividing by tens. In fact, I'm going to be dividing by 10 4 times. Because if I do that, that's going to move it out of there. That's 1, 2, 3, 4 times. So times 10 to the negative fourth. Remember, negative powers are equivalent to dividing by 10. So I just divided by 10 4 times. And this is the number of Skittles that you're consuming per second. You can't even taste them. They're not really Skittles. It's more like Skittle dust. But S-K-I-T-T, there's another L in there, L-E-S. All right, that's that question. On to, I think, our last page. This last page says, hey, graph each equation, identify the y-intercept and slope of each line. This first one, the slope is clearly 3/2, right? I didn't have you do a lot of complicated things to get that. It was already pretty much in slope-intercept form. The y-intercept is -4. The next equation is not in that same format, right? But I can make it that way by just subtracting 2x's from both sides. So it becomes y is equal to -2x plus 6. So now I can see the slope for this is -2, and the y-intercept is +6. And we're asked to graph them. So if these are each worth 1 unit, I have to go down to 1, 2, 3, -4. And then I have a slope pattern of up 3/2, up 1, 2, 3/2, 1, 2, 3. And it can be a little tedious, but I'm going many points here. just because it's difficult to draw an accurate line when you have just points that are very close to each other. So after drawing many points, right, I can line my ruler up, and I think I can hit that pretty well by just drawing that line through there. So that's a fair representation of this line. Then the other, I just did. No, I did the right line. I did a y-intercept at -4. The next line has a y-intercept way up at +6, right? 1, 2, 3, 4, 5, and 6. I got a dot here at 6. And it has a slope pattern of -2, so I'm just going to decrease. Before I was increasing by 3, but did I do that? Yeah, I did up 3 over 2. Now I have to decrease by 2 and go over 1, down by 2, 1, down 2. There's my x-intercept. That's nice. Down 2 over 1. All right. And once I have enough of those, I'm just going to line up my ruler and draw it all the way to the ends. You can see I'm kind of getting off of that line near the end. So I would be very careful if I really depended on getting working information from that. I'd maybe extend those lines out more. All right, next question. We are asked to write a rule, an equation that matches this graph below. So on this graph, one of the things that I see is it goes through the point where x is -5 and y is 7. So am I right? Hey, this is an x and this is a y. And I have a slope of an m value of 4/5. Now I look at this and it looks like it's going through a very nice spot, right? It looks like I can clearly see what that point is. Or can I? Could it be that it's actually close to that, but it's actually not that value? So I'm not going to risk it. I'm going to go ahead and plug this information into the point slope format, which I'll just as a reminder, y minus the y value that I know is going to equal my slope times the quantity of x minus the x value that I know. So I'm going to start by plugging in my known y value, which is +7. So I'm going to write y minus that +7 equals my slope, 4/5 times the quantity of x minus -5, right? My known value of x was -5, so I had to subtract that. If I distribute and add 5, right, I get y is, it's going to be +4/5. And then this is going to be a +5. And if I have 5 times 4/5, it's going to be a plus, oh, I'm sorry, there's an x here. This was 4/5 x. And I'll just write this, and then it's going to be plus 4/5 times +5, and then plus 7 from the other side. So I did two things. I distributed the 4/5 to both terms inside these parentheses, and I also acknowledge that when I multiply this negative times a negative, it becomes a +5, and I added 7 to both sides. 4/5 times 5 is just 4, 7, 8, 9, 10, 11. So this becomes, really? I have to be wrong. I have to be wrong. There's no way this is correct. 4/5 x. I have to be wrong. There's no way this could be correct, because this would be 4 plus 7, 7, 8, 9, 10, 11. There's no way the y-intercept's at 11. I have to be wrong. What? What did I do? Oh, what did I do? Oh, what did I do? There's something clearly wrong with this. And then I realized, well, maybe nothing is wrong with this. Maybe the problem is the picture is wrong. And this is really quite different. So if I look at this, right, this says that x is at the point -5, which I like. I think we've got that -1, 2, 3, 4, -5. But then why is it +7? So the problem is this image I gave you is deceptive, right? But if I work with what's known, that it goes through apparently negative 5, 7, and it has this slope of 4/5, I end up getting, and I don't want to believe it because I'm looking at the picture, I end up getting y is equal to 4/5 x 7, 8, 9, 10, 11 plus 11. Which means that this point, negative 5, 7, would actually be up here. 1, 2, 3, 4, 5, 6, 7. This point would live here. And if I was at that point and I continued to do the up 4 over 5, up 4 over 2, 3, 4, 5. Yeah, if I did from there up 1, 2, 3, 4, and I went over 1, 2, 4, 5, I would be at 11, right? I would have a y-intercept of 11, which is exactly what I'm seeing. So if this is the point, it says write the rule that matches the graph below. Does it match the graph below, or does it match the slope of the point below? Whichever one it does, something's not right in this picture. And I like that. And maybe this is the kind of question that should be considered a bonus question, because there's definitely some conflict here between what it says and what it looks like. Okay, the last question I asked you to do was to write at least 3 single-term expressions that are equivalent to the one I gave you. And I'll just say one of the things I saw many people do is just write 2y over x to the positive second power, and that's great. I also saw people just say, hey, look, I have to have 2 at the end, so I could go 2 over 5, and I could make this, I could make it 5xx, and I could put y up there. That's the same. Those are equivalent. And I didn't say that you couldn't use negative exponents. I just said they had to be equivalent. And something else I saw someone do was they left a 2 up here, and in the bottom they placed y to the negative first and then x to the second power. So all 3 of these are equivalent to each other, and regardless of the value of x or y that you select, they would all produce the same outputs if you plugged in those x and y values. All right, so that's it for that study team test. I really like this question. I like that. Maybe you didn't. I think I was pretty lenient with it. But if you gave me the equation that went just based on how it looked, I gave you points. But I think if you gave me this equation when I graded it, I'm like right on, and I gave you extra credit because this, if it's going through the point negative 5, 7, it's not what I see graphed. It should be, well, I can draw the other line. It should be a line way up here, roughly. I'm grabbing my ruler. Something, well, I guess it should go through those points, something like that. All right, anyways, I hope you have some time to consider these things, think about these things, and I look forward to seeing you on Friday when you take your chapter test.